evening, everyone. We are in the week 6 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 6 is about small signal performance analysis. I am Teja Golla, a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen?
Not yet, sir. We'll let you know.
Okay.
Now I can see.
Okay. So the week 6 is about, as I have discussed in week 5. So week 5 was about how to get the equivalent model, AC equivalent model, DC equivalent model, or in general, I can say overall equivalent model. And week 6 is about getting something from this equivalent model, basically transfer functions or some other information, so that we can use this to design the controller. Because as we have discussed, that was our final objective of this course, to design a controller that will make sure the converter runs so that it will meet the required performance, transient performance, or whatever is our objective or whatever is our requirement. So we have started with the modeling in week 5. Now using that modeling, we'll be discussing about what are the different transfer functions, so that we can use those transfer functions in the upcoming weeks to design the controller. So I'll just quickly go through what we have discussed in week 5, because it is connected to what we'll be discussing now, so that it will brush up what we have discussed and we can directly use the results that we have obtained in the week 5 directly in week 6. So in week 5, we have discussed about different types of methods to get the small signal model. One being the circuit averaging, another being the average switch model. All the both are similar, and towards the end we have discussed about the state space averaging. As I have mentioned, in these two methods, we can actually see the circuit and we can see which resistance or which element is corresponding to what term in the transfer function and how things are getting affected. Whereas in the state space averaging, it is more mathematical, but it will be easier if the order of the system increases. So first we have discussed the circuit averaging. So where we have written the dynamics and then applied the averaging and then perturbed it around an operating point. And then we have considered one approximation. So the approximation is product of two perturbed terms is negligible. So this is one assumption, and the other assumption is perturbation is small. So only if the perturbation is small, the product of the perturbations will be much smaller and it can be ignored. But if the perturbation is not small, then this approximation may not be valid. So in all the modeling or analysis we do, sometimes we consider some approximations. So that approximations are valid under certain conditions, like the perturbation is small. So if that condition is not valid, then this assumption is also not valid. So we will discuss regarding this when we come to model validity. Because we have considered an assumption, the model may not be valid in all the conditions. So it has some validity. So how much it is valid, how it is going to affect the controller performance, all these will be discussed in the upcoming weeks. But just take a note of this, because we have made assumptions, considered assumptions in the process, and that will put some limitations on the model, which we'll be discussing in the upcoming weeks. So from the inductor, we got this equivalent model. Same thing we have done for the capacitor, and we got the model. And input current also we have done the same thing. And now we have combined all of them, and we have put a transformer model, because the relation is like a transformer. So we have put a transformer which has both DC as well as AC components. So that's why this representation. In the case of average switch model, we have considered the switch, and then we have applied the averaging on this switch, and then we got the model, and then we have connected the rest of the circuit, and we have seen both are resulting in the same circuit. And then we have solved few problems regarding the DC equivalent model, and how we can get the voltage gain expression using the DC equivalent model, as well as the efficiency. And then we have also solved a few problems where I have given certain values, and we have asked what will be the duty ratio to achieve this model, because it's a practical buck converter and it has some parasitic drop. So we have obtained the equation, and then using that we have solved the problems. Towards the end, I have also mentioned state space averaging, where we'll obtain the state space, and then we'll apply the averaging and perturbation on the state space, and then we'll apply the same approximation. We'll ignore the higher order, second order terms. So product of two perturbation we have considered to be 0. So the assumption is same in all the methods. So we'll get the same model in all the methods. So here also we are considering perturbation of, say if B1 is not equal to B2, D perturb into V in perturb is considered to be very, very small. So that's why it is ignored. And if the perturbation is not small, then it cannot be. And then we have obtained the final expression for the AC equivalent model. Also, we have discussed how to get the DC operating point. And then we have also seen how to get the output voltage V naught perturb in terms of the state X perturb. So this is what we have discussed in the previous week. So now I'm going to start this week discussion from the equivalent model that we have updated in the last week. So this is for a practical buck converter. So we have the input perturbed around the operating point V, and the other terms are what we have obtained in the process of averaging and perturbing the dynamics. And these are the inductance, capacitance, as well as load R. And if there is a current source, then I can also add something like this here. So there is a constant current source. So load can be anything, constant resistive, constant voltage, or constant current. So here I'm considering a constant current I naught plus I naught tilde. Okay. So is this clear until this point? I have just summarized what we have discussed in the previous week. So if things are clear, then we can proceed. If you have doubts, then I'll clarify that before proceeding, because this is very much important for today's discussion. If you have any queries, you can ask as we'll proceed.
It's clear, sir, till this part.
Okay. So now, if you see in this circuit, there are some DC terms as well as there are some AC terms. So we have discussed for the DC equivalent model, we have to remove the AC perturbation terms. So we have removed the AC perturbation terms and then we got the DC equivalent model. So now here I am asking, draw the AC equivalent model of the buck converter with parasitic. So overall model I have given. So if now I am asking the AC perturbed or AC equivalent model, so what should I be doing? Anyone?
We can set the DC values to 0.
Yes. So because I am asking only AC equivalent model, so we are perturbing or a equilibrium point, and that equilibrium point we will shift to the origin basically. So basically we are removing the DC equivalent model separately from this, and then we'll get AC equivalent model as well as DC equivalent model, two models. So what I mean to say, so this is the overall model, right? So this is the overall model. And then this has two components. One is the DC equivalent model. One is the AC equivalent model. So how DC equivalent model is helpful? We have seen in the previous week. It is helpful to get the steady state or operating point. Operating point at steady state. So I am representing steady state as SS. And we have also seen we can get the details regarding the efficiency. So if we want to see what is the efficiency at which our converter is operating, then we can use the DC equivalent model and calculate the efficiency. Also, if you want to calculate some losses, you can also calculate the losses from the DC equivalent model, because they are all steady state 10 models. Now coming to the AC equivalent model, why they are needed, we'll see that they are needed to get the transfer function. So in this week, we are going to learn how to get the transfer function. And in the upcoming weeks, we'll also see controller design, how this will be used to get the controller design, and also performance, transient performance. So these are the application of these two models. One is the DC equivalent model and one is the AC equivalent model. So in the previous week, we have discussed about the DC equivalent model efficiency, also losses and operating point like duty ratio, what else, the output voltage, etc., etc. So now this week we are going to discuss about the transfer function. Upcoming weeks we'll discuss about the controller design and how the transient performance will be affected for different types of controllers. So as I have asked AC equivalent model, I will remove the DC operating point. So here we have one voltage source. Here we have one current source, dependent current source. Here we have transformer. Here we have one voltage, dependent voltage source, and then we have inductor. We have equivalent resistance, and then we have ESR. We have capacitor, and then we have constant resistor load, also constant current flow. Okay. So if we want to write, this will be V in per. This is a transformer. Now it is AC equivalent model. So I'm only denoting the AC symbol. Turns ratio is 1:D. This is inductor L. This is RE, and this will be IL per. This is RC, C, R. This is I naught per, and the voltage is V naught per. And then what am I missing? This is D per by L. This is D per V. So this current source is D per into IL, and then this is D per into V. So this is the overall AC equivalent model. Just let me know if I'm making any mistake. I think, yeah, RC and CR. Yeah, everything is fine, right?
Yes, sir. Looks fine.
Okay, so now this is how we get the AC equivalent model. Similarly, we can do for boost converter and buck boost. I think Calvin has explained regarding the boost converter AC equivalent model during his session. So now using this AC equivalent model, now we are going to discuss about how to get the transfer functions. So if things are clear till this point, I'll move further. If you have any queries, you can ask.
Clear, sir.
So now I'm asking, write the expressions for the following transfer functions of an ideal buck converter. So as I have said, we'll be using the AC equivalent model. So let us just copy what we have obtained. And because I have mentioned the buck converter as ideal, why? Because it makes things simpler. So I have given this question so that it will be used to understand regarding the importance of these transfer functions. And in the upcoming question, we'll solve for a practical buck converter where we can understand how the parasitics are going to affect the transfer functions. So because I have mentioned that it is ideal, so parasitic resistance will not be there here as well as here, and rest remains same. So, okay. So this is the AC equivalent model of a ideal buck converter without any parasitic. Now I'm asking what is the input impedance. So whenever we are saying something about transfer function, the very first important thing that we need to understand is the expression for the input impedance. Not input impedance, expression for the transfer function, because transfer function has some output, some input, as well as some condition. So we need to understand, or we need to first write the expression for the transfer function in terms of those input and output as well as those condition. Then we have to redraw the circuit, and from that circuit we can easily get the expression. So these are the steps that we need to follow and we'll be following to get the expression. So can anyone tell me what is input impedance?
If we look at the impedance from the V inside,
Yes,
like
from the input side. Yes. So yeah, if we look at the impedance from the input side, that is input impedance, and from the output side, that is output impedance. But also there is few conditions that we need to follow. So let me write. So we'll go step by step. First one is the input impedance. So let us write the expression. So input impedance is defined as Z in of S, which is V in per top of S by I in per top of S at other perturbations are zero. So D perturb is zero as well as I naught perturb is also zero. So the ratio of V in perturb of S with respect to I in perturb of S, when the D perturb is zero as well as I naught perturb is zero, then this expression will give us input impedance. So now if D perturb is zero, what happens to this current source? Dependent current source
becomes 0.
becomes zero. So there is no current flowing in this path. So it can be removed. Similarly, what happens to this voltage source?
It gets shorted.
It gets shorted. So this is also shorted. So basically I can remove this and short, I can remove this and open, and I naught tilde is also zero. So this current is also zero. So basically I have input here and a transformer here, 1:2 D turns ratio, and then I have impedance over here. So every time whenever someone is asking the transfer function, the very first thing we'll do is we'll write the expression and then we'll redraw the circuit, because this circuit will look complicated. But once you redraw it, majority of the elements are gone. So it will make things look simpler so that we'll not make any mistake. So always like my practice is to redraw the circuit. So we have and the concepts that we are learning are generic. It is not applicable only for buck converter. We have considered buck converter to be our case study, but for any converter, input impedance is this. So accordingly, we have to draw the its AC equivalent model and then obtain the transfer function. So this is our V in perturb. So this will be our I in perturb, and this is the turns ratio of the transformer 1:D. And now we can write everything in Laplace domain. So this will become SL, and this will become 1 by CS, and this will become R. So now, if this is V in, what is this voltage? Here,
D into
D into
D into
VN.
V.
D into V in, very good. And the current?
IN by D.
Yes, I in tilde by D. So now I can apply KVL. So I can write, or basically be equal to impedance into current. So we get D into V in tilde is equals to I in tilde by D into impedance is SL plus R parallel 1 by CS. Agree?
Yes.
So I have considered this as R parallel 1 by CS, and that is in series with the SL. So that will become this expression. So now if we simplify further, we will get V in tilde by I in tilde equal to 1 by D square into, if we simplify this, we will get SL plus R into 1 by CS by R plus 1 by CS. Right?
Yes.
So if I skip the term, so if I multiply by CS on numerator and denominator, I will be getting R by 1 plus SRC. So I think it would be good if you also start like calculating along with me, deriving along with me, then it would be also beneficial for you. So if you have book and pen, you can also derive with me. Then you'll also feel comfortable in deriving these expressions. Because ideal case it is easier, but as we go to non-ideal case, it will become more difficult. So practice is the key. So if you derive it once, then you'll feel comfortable. Okay. So this is the overall expression. Now, if we multiply and simplify, I can get V in tilde by I in tilde equal to. So in the numerator, I will get S square LRC plus SL plus R by A square into 1 plus SRC. Clear?
Yes.
So this is the overall transfer function that we are getting. So this is our Z in of S. So this is our Z in of S, which is S square LRC plus SL plus R by D square into 1 plus SRC. So this is how we will be getting the input impedance, where first we have written the expression and then we have simplified the diagram. So this has many components, but if you see this has only three, which are again becoming into single impedance. So basically it is impedance by D square because of the transformer turns ratio. We are getting 1 by D square, and this is the actual impedance of the buck converter output side, which is inductance in series with capacitor and resistor which are in parallel. So is this clear until this point
Yes, sir. Clear.
for everyone, Arun and Naveen as well?
Yes, sir, it is clear.
So now we have to add one more page. So till now we have discussed about the input impedance. So now we are going to discuss about the output impedance. So can anyone tell me what will be this expression for output impedance? If we write in similar
Uh,
fashion.
V naught by I naught, keeping D cap equals to 0 and Vn equals to 0.
Yes. Good. But one slight modification and important thing also. So we are discussing about output impedance. So we have Z output of S, which is V naught tilde of S by I naught tilde of S at V bottom equal to 0 as well as V in bottom equal to 0. So the one modification is, if you see the current is sinking, not sourcing. So basically, when we are saying any transfer function is, we are exciting the converter of the circuit with I naught of S. So you are supplying I naught of S to the converter and you are saying what is V naught tilde of S. Basically, you are perturbing I naught and then checking how much is the perturbation in the V naught. So basically, you are giving I naught. So I naught should be source. But if you see here, I naught is sink. So the sink, how can it be made to source by putting a negative sign? So that's why we'll have one minus sign over here. Is that clear? It is very important why we have a minus sign over here. So that's why I'm using a different color. Basically, when we are exciting something with a current, it should be current source, but the current that we are having here is current sink. So that's why there will be one opposite side that will result in a minus here. Is that clear, or do you have any confusion?
Sir, current is going from right to left, which is opposite of the conventional norm. That's why it's minus or
Yes,
something
yes,
else.
yes, yes, yes. So basically, when we are discussing or getting the output impedance, so we need to supply to the, this is the output impedance, right? So basically, uh, we are seeing from this side. So we are viewing from this side. And now I want to find the Z out from this side. So basically what I will do is I will excite it with a current source I naught of S. And then I will see what is the perturbation V naught tilde of S. But in my circuit, I don't have I naught like this. I have I naught like this. So what I'm going to do is I'm going to put a minus sign. So I can say this is my I naught tilde of S. I can reverse the direction and I can say this is minus I naught of tilde. Because in my circuit, I naught is sinking. I need source. So that's why what I'm doing is I'm putting a minus sign here. Because I'm treating in the opposite direction. Because my I naught should be source. Basically, what we are doing is instead of having minus here, we are having a minus here because it's a source. But both are same, so that's why we are writing it here. So this is somewhat tricky and where people make mistakes. So that's why I'm stressing here. Our I naught should have been source, because whenever we are exciting something, you should supply current to that something. Say here converter, and then you have to see the response, which is V naught. So you have to give the current or supply the current to the circuit, which is this circuit, but instead you are drawing the current. So if we are drawing I naught tilde, it means we are supplying minus I naught tilde. So that's why we will have a minus over here. Is that clear?
Yes, clear, sir.
Also, maybe I'll consider one simple circuit. Then it will. So say this is a resistance and this is current. Say this is R. This is say I naught. And this is plus minus V naught. So now can you tell me what is V naught in terms of I naught and R?
Minus I naught into R.
Yes, minus I naught into R. So now my minus V naught by I naught will be R, which is same as this circuit. I naught dash R plus minus V naught, and I have now V naught by I naught is R. So I naught dash. So either I should supply it with a current I naught dash, or I can sink a current of minus I naught. Because of the direction of the current, I am putting a minus sign. But if I basically see the impedance in both the cases, looking at the circuit, I can say the output impedance is resistance R. But mathematically, if you see, I have to deliberately put a minus sign here because here I am sinking the current, whereas here I am supplying the current. So that's why this minus sign comes over here. Clear, right?
Yes, sir.
Oh. So now basically D tilde is 0, B in tilde is also 0. So if D tilde is 0 and B in tilde is 0, so what will happen? Which terms will become 0? D tilde and B in tilde.
Transformer primary will be short circuited.
Which one? Which one? Which one will be short circuited?
We can say transformer primary
Yes, yes,
short
yes,
circuited.
yes.
So similarly,
That
secondary
VN
is
part will be shorted, yeah.
Yes, yes. So this V part will be shorted and this will be open. So if the primary winding is shorted, I can short the secondary winding. So I can replace the entire transformer by a short wire. Yeah. And anything else? What about this D tilde into V?
D
Shorted.
tilde Vn is also same.
Shorted. So basically entire thing is shorted. So we have an inductance in parallel with resistance, in parallel with capacitance, and output we have I naught tilde. Okay. So let me redraw the circuit. So the entire circuit will become something like this. Inductance parallel with capacitance, parallel with resistance, parallel with sinking current I naught. So this is my SL, this is my SC, this is my R, this is my I naught tilde, and this is my plus minus V naught tilde. So now what I will be doing is I will consider this entire thing into a single impedance. Say I want to consider this as an impedance Z. So now this Z will become my output impedance because basically I am converting this entire thing into this circuit. So my Z will become my output impedance. So now I have to calculate what is my Z. So what is Z here? Anyone?
SL into 1 by CS into R divided by SL plus 1 by CS plus R.
Uh, okay, I'm not sure. So basically, you are saying
Like
all
parallel.
all will be parallel, right?
Yes.
Okay. So now we'll simplify one by one. So if I consider 1 by CS parallel R, then I'll get R into 1 by CS by R plus 1 by CS. So if I multiply by CS on numerator and denominator, I'll get R by 1 plus SRC, right?
Yes.
Now my Z will become SL parallel R by 1 plus SRC. So now I will get SL into R by 1 plus SRC by SL plus R by 1 plus SRC. Agreed?
Yes.
So now if I simplify further or multiply by 1 plus SRC on the numerator and denominator, I will get SLR by S square RLC plus SL plus R, right? Is this clear?
Yes.
Okay. So now I can
Concept.
write my Z out of S, which is Z here. So Z out of S is nothing but what we are getting here, which is, say if I write like this, SLR plus S square RLC plus SL plus R. So this is my output impedance. So how did we calculate the output impedance? We have understood first the definition of output impedance, which is minus V naught tilde of S by I naught tilde of S, because I naught here is sinking and not sourcing, and that will lead to that minus sign. And then we have to get this expression when D tilde is 0 as well as V in tilde is 0. So if V in tilde is 0 and D tilde is 0, this will be open, this is shorted. So this will be shorted. Also, this is shorted. So basically this entire thing is represented by one shorted wire. So SL is parallel with 1 by CS is parallel with R. So the effective circuit will become something like this. And now we can get V naught tilde by I naught tilde, which is the minus I naught tilde, which is the effective impedance over here, which we have calculated, and we got this expression. So is this clear until this point?
Yes, sir. Clear.
So now if we proceed further, and then if we move on to another transfer function, which is audio susceptibility. So can anyone tell me what is audio susceptibility?
Output V naught by like perturbation in voltage versus perturbation in current, input current.
Input current or input voltage?
Input voltage.
Voltage, yes.
Input voltage, my bad.
Yes, so output
Yeah.
voltage by input voltage, which is also called as line regulation. So whenever there is disturbance in the input, how much will the output get affected? Because that should not get affected. So we have to see whether there is any direct correlation from input to output or not. So this is represented by GVG of S, which is again V naught tilde of S by V in tilde of S when there is due to ratio perturbation and I naught perturbation equated to 0. Okay, so now which terms will become 0 in this? D perturb is 0 as well as I naught perturb is 0.
Current source open circuit.
Okay, and
The
this one shorted,
dependent
right?
voltage source is shorted. Yes.
Okay, and the output is also open, this current source.
Yes.
So let me first draw the circuit. So always like safe side to draw 4 different circuits for calculating 4 transfer functions so that we will not make any mistake. And also the circuit looks simple. So this meeting might end in a minute. If this ends, kindly join back. We'll continue our discussion. We have inductor, we have capacitor, we have resistor, and output load current is open because I naught tilde is 0, R plus minus V naught tilde 1 by SC, SL. This is 1:2. This is V in tilde. So what will be this voltage plus minus? If this meeting ends, kindly
D
join
into
back.
Vn.
Yes, D into V in tilde. We already know. We already have calculated that this impedance R parallel 1 by SC is nothing but R by 1 plus SRC. So I can replace this entire thing by a impedance, and the value of that is 1 plus SRC. Clear? So this SL is in series with R by 1 plus SRC. Any doubts how this simplification is done? I am basically representing this entire thing by one impedance, which is R by 1 plus SRC. So SL is in series with R by 1 plus SRC. Is that
Clear, sir.
Okay. So now I need V naught perturb by V in perturb. So basically, first I will be calculating V naught perturb by dV in perturb. So what will be the expression of this?
R by 1 plus SRC divided by SL plus R by 1 plus SRC.
Yes, very good. Basically, we can consider as an impedance divider. So there are two impedances in series like SL as well as R by 1 plus SRC. So the voltage will be divided among these two impedances, and we are bothered about the voltage across R by 1 plus SRC. So Z2 by Z1 plus Z2. So now if we multiply by 1 plus SRC in the numerator as well as denominator, we'll get R by S square and RLC plus SL plus R. And if we bring the D this side, we'll get something like this. So GVG of S is D into R by S square RLC plus SL plus R. So this is the audio susceptibility. Now I have a question. Say I want to calculate GVG of S at zero frequency, say S equal to zero. So what is the expression or what is the result that we'll be getting?
D.
D. Because if S is zero, R by R will get cancelled and we'll get D. So it means that there is a direct relationship between input as well as output at zero frequency. So when the frequency is not there, it's like DC point, right? So V naught is nothing but D into V in, which is what we already know for a buck motor. So that is the input output relationship when the frequency is zero, which means DC. So that's how we are getting the relationship between the input and output. So if the frequency is more, then the input and output relationship will vary depending upon the frequency. And if you know, this is a low pass filter. So the dependency or the like gain factor will keep on reducing, but at DC point it is D. Further, it will be smaller and smaller. So that's what we are getting from this transfer function. Is that clear?
Yes, sir. Clear.
Now, if we go for the final transfer function, which is the control to output transfer function. So anyone, what is control to output transfer function?
V naught by D.
Yes. So very good. Control to output transfer function. As we can see, control is what? The control variable is duty ratio because we are trying to control the duty ratio, which will regulate the output voltage. So control to output is D to V naught. So control to output transfer function is GVD. So we have GVD of S is equal to V naught tilde of S by D tilde of S when V in tilde is zero as well as I naught tilde is zero. Okay. So let us go back to the original diagram. So V in tilde is zero and I naught tilde is zero. So first of all, I naught is gone and D tilde is not zero. So which term will be zero?
Vn will be 0.
Yes. So this is shorted.
Yes.
And if this is shorted, this is also shorted. And we are not bothered about what current this is drawing because if this is shorted and we are only bothered about the voltages, current will not come into picture. So we can ignore this because this is basically shorted. And if we apply KVL, then this current expression will not come into picture. Is that clear?
Yes.
Okay. So now basically we have this voltage source and here one impedance and here another impedance. So instead of here we had D into V in per term, now we have V in into D per term. So if I redraw the diagram, I will have something like this. So this is the polarity. Careful with the polarity. So this is V in into D tilde. And as the current source is shorted and it will not appear in the KVL expression, we can ignore this. Although it is there, it is shorted. So the current source is basically shorted and that will not affect the expression because we are applying KVL and it is shorted. So that's why we have ignored this, but this is there. It does not mean that it is not there. But in our calculation, it is not related. So that's why I have not drawn in the final figure. So if you see basically here, we have this expression. So both are same, right? Here input is dv in, there it is v in into d. So I'll just copy paste this because everything remains same. So basically this is r by 1 plus src, and then this will vary. Instead of d into v in, we have v in into d part. So now if I bring the v in here, so now if I write the expression similar to like this, or how we have written, the d will be coming here. Instead of d, we'll have v in coming over here. So I'll have gvd of s equal to v in into r by s square rlc plus sl plus r. So like both are same. If you see, gbg has d and gvd has v in, because v not equal to d into v in. So similarly, if you calculate gvd of s at s equal to 0, which is dc, you will get v in, which means v naught by d is v in. Here also you are getting the same, which is v naught by v in equal to d. So both are basically same. Is this clear until this point?
Yes, sir. Clear.
So in the first problem, we have obtained the AC equivalent model by removing all the DC terms, and using this AC equivalent model, we have obtained the expression for 4 important transfer functions, which is input impedance, and the expression of which can be written something like this. So the conditions are very important because these conditions will remove some of the elements in the circuit. So these conditions are also very important. So Zn of S is nothing but V in tilde of S by I in tilde of S when D part and I not part are 0. So always you have to remove the terms and then redraw it and then get the expression. So Naveen is asking how you get the condition. So basically this is how it is defined. Input impedance is what? The impedance that you see from the input side. So your excitation is say I in. So you are giving some I in input and then you are observing V in input. So when you are giving this excitation, all other perturbation in the circuit should be made 0, which are basically D perturb and I not perturb. So that's why we are making these two 0. Similarly, in the case of output impedance, we are seeing the impedance that we see from the output. So we are exciting it with a current source and checking the voltage here. And then all the perturb terms that are inside the circuit should be made 0, which are D perturb 0 as well as V in perturb 0. So if it has any other extra perturbation, that also needs to be made 0. But in this circuit, we have only 2. So that's why these are made 0. So in the input impedance, we have V in by I in perturb. And if you see, I in perturb is entering. So I in is kind of source. So that's why we have plus sign. Whereas I naught is leaving the circuit, which is sinking. So that's why we have minus. So Z output of S is defined as minus V naught tilde of S by I naught tilde of S when D perturb is 0 as well as V in perturb is 0. And then we got the expression. Similarly, audio susceptibility is defined as V naught tilde of S by V in tilde of S when D perturb is 0 as well as I naught perturbation is 0. and then we redraw the circuit and we got the expression. And we have also seen at DC, the input and output voltage relation will have a ratio of D. That's how it should be for a buck converter, and we are also getting the same expression. And control to output transfer function is similar to audio susceptibility, except here we have d perturb with the denominator and v in perturb at I naught perturb at 0, and we got this expression. And we have also seen at DC, the relationship between the ratio between the output voltage and duty ratio is V, and which is what we are supposed to get. And we have gotten this for a buck converter. Similarly, for boost converter, we'll get a similar expression, but it has something called RHP0. So that will come on the numerator. I think Kelvin might have explained. So that's why boost has some additional problems like control challenges, whereas buck doesn't have. Is that clear until this point?
Yes, sir.
So now let us move on to another question. So the question remains same, except certain changes. So we are asking, write the expression for the following transfer function of a practical buck converter. So let us go back to the original circuit diagram that we have obtained. So this will be the circuit diagram. So I'll not be deriving, but I'll be giving you hint, or we'll discuss how to derive. So now things will become a little bit complicated because of the presence of the parasitic. So this is the AC equivalent circuit of a practical buck converter. So this is the AC equivalent model. AC equivalent model of a practical buck converter. So now we have to calculate the input impedance. So basically we can copy paste the circuit because we already know the expression. So now what happens? Let me just copy paste this so that our time will be saved. So we are starting from the input impedance. Okay. So now what additional terms we'll be having? So we'll modify this. Here we have something. So here there is impedance and equivalent resistance, capacitance, resistance. So this is SL, this is RE, this is RC, this is 1 by SC, this is R. Clear?
Yes, sir.
Now if we see the expression over here, the input impedance, we got something like this. dV equal to this. Now the expression will not be simpler because we have some additional parasitic. So instead of SL, we have SL plus RE plus 1 by SC plus RC parallel resistance R. So if you simplify, it will become a complicated expression, and sir has simplified it into poles and zeros. I will not be solving because that is a math that you can do. So I will be skipping that part so that we can discuss another concept regarding the current mode control. So I'll not be going in detail, but this is the final expression. So that is just a simplification of this expression. But I write the final expression in terms of these terms. So we'll get Z input of S equal to 1 by d square into 1 by d square into SL plus RE plus 1 by SC plus RC parallel R. So in the previous case, we didn't have RA. Also, we didn't have RC. So the expression will become slightly simpler. Now it becomes a little bit more complicated because of the effect of RE as well as RC. Is this clear?
Yes, sir. Clear.
Okay. So now we'll move to the next term, which is the output impedance. And we can also copy the definition as well as the circuit. So this is the circuit. So now if you see SL and 1 by SC has some parasitic resistance. So we need to include those. So we have RE, SL, RC, 1 by SC. So this is the final modified circuit, right?
Yes.
So now the effective impedance, if I call it is Z, I can write as V naught tilde minus V naught tilde by I naught tilde of S is nothing but the effective impedance Z. So now if we write the expression of Z, which is basically Z out of S, then we will get RE plus SL parallel RC plus 1 by SC parallel resistance R. So this is the expression that we will get. So in the previous case, we didn't have RE as well as RC. Now we got two additional terms. So that will increase the number of terms and it might lead to few additional poles as well as additional zeros. But if the values are smaller, then the poles and zeros will be far away from the imaginary axis, so they will not have any impact. In that case, you can ignore them. But if the value of RE as well as RC is significantly higher or relatively higher, then they'll come close to the imaginary axis and then they will have effect on the or impact on the response of the system. So depending upon the value, sometimes we can make the assumption like ignoring them because they are farther away and they'll not have much impact. But sometimes, depending upon the rest of the location of the poles and these poles, we might have to consider if they are close to the imaginary axis. So is this clear till this point, output impedance?
Yes, sir. Clear.
So now let us go to audio susceptibility and then we can copy it in this file. So again, audio susceptibility, we have two more additional terms. Here we have one additional resistor. Here also we have one additional resistor. Sometimes resistance, capacitance, SL, RE, RC, 1 by SC. So now again, we can simplify, but now this simplified expression is no more valid because we got one additional term. So now, if I directly write GBG of S, we know that it has term D because the D is coming from here into the impedance of the effective impedance here by summation of this impedance plus this impedance. So if we write the expression in the denominator, we have SL plus RE plus RC plus 1 by SC parallel R. In the numerator, we have RC plus 1 by SC parallel R. Is this clear?
Yes, sir.
So, like as you can see, the like terms are getting more complicated depending upon the parasitics, but all of them have similar denominator. So the denominator remains same, just like in the previous cases. If you see here S square RLC plus SL plus R, here S square RLC plus SL plus R, here also S square RLC plus SL plus R. Here that you will get in the input impedance only, you will get that in the numerator S square RLC plus SL plus R. But the other three transfer functions have the same denominator. Similarly, here also the denominator will remain same if you calculate and see. But that is a little bit more lengthy, but you can do it as your homework. And sir has given the final expressions, so you can always correlate with what whether you are getting what sir has given or not. So this is audio susceptibility. Now the last transfer function is the control to output transfer function. So this is also quite similar to audio susceptibility, except instead of D, we'll have V in. Okay. So now let us write. So this is our RC 1 by SC RE SL, and of course this will not be valid anymore. So now we need V naught by D tilde. So I can directly write the expression which will give me GVD of S, which is equal to similarly we'll get V into one expression which is actually same from here. So this is the expression because that term remains same, only because the circuit remains same except the first part. So this is what we got. And hence both will have same numerator and denominator. Only difference is there we have D into the transfer function. Here we have V into transfer function. So both are quite closely related. So is this clear? So we have discussed about all the four transfer function for ideal buck converter first, followed by practical buck converter.
Yes, clear, sir.
So if you have any doubts, you can ask. Else we'll move to the fourth problem of today, which is also simple. Then we'll move to the final topic.
Sir, one doubt regarding
Yes.
from examination point of view.
Okay.
If we know the steps to derive the transfer function, is it sufficient, or do we have to memorize those final standard formats? Otherwise, we can do like this.
Yes.
Because if the options are given in standard formats, then we have to convert it like that.
Yes. My suggestion would be don't memorize the results. Never do that, at least in this transfer function case, because there can be several scenarios where I will change this, I will change that, and the final transfer function will vary. If you quickly get this circuit, like this is also very simple, as we have discussed previously. You have to write the dynamics, and from the dynamics you can get this expression. And once you get this, you can as you have seen, it is very simple to derive the expression from the circuit. Only you have to see the definition and then make the rest of the perturbations to zero and redraw the circuit. Once you redraw the circuit, get the expression and then simplify the expression. So if you are like comfortable with solving this expression, this might look little bit like complicated, but if you solve it once or twice before going to the final exam, then you will be more comfortable with solving. Then it will become very simple. You just have to uh, solve it by yourself, which might take few more minutes than memorizing the circuit. But if you memorize the transfer function, you will eventually forget after this course. But if you follow the method, then you will remember, and the same thing you can apply for other converters and you can still do. So always go with the conventional method of deriving. Sometimes, in some cases, not in this week, you need to memorize certain things so that you need not derive the entire expression each and every time. In those cases, you have to memorize. I think till now we might not have come across such scenario, but if there is something that you need to memorize, I'll like highlight it so that you have to few things. Like in all the courses, there will be certain formulae that we need to remember, so that will save a lot of time. But this much big expressions not needed. Like if you see omega RHP of a boost converter, that you can memorize. That it will be difficult for you to every time derive. So that will become much handy if you memorize that omega RHP expression of a boost converter, which is simple. But if I ask you to derive the control to output transfer function of a boost converter, it may be difficult for you to memorize. So in that case, derivation is a better choice. So it's depending upon the situation. Sometimes we have to memorize, and sometimes we have to derive.
Okay, sir, clear.
So if you don't have any further queries, then we can go to this another question where I'm asking, draw the small signal block diagram of a practical buck converter with the following transfer functions: input impedance, output impedance, audio susceptibility, control to output transfer function. So first of all, did you understand the question? Did you understand what is small signal block diagram?
The block diagram that we have developed in initial weeks for RLC circuit.
Like yes. Very good. So we have to draw a similar block diagram, but we'll be using transfer functions as the block. So we'll be using input impedance, output impedance, audio susceptibility, as well as control to output transfer function blocks, and then we'll combine everything. So so input impedance. Let us start with the input impedance. So if we write the input impedance as a block, which is Z in of S, what will be the input and what will be the output?
I in will be the input and V in is output.
Yes, I in tilde of S will be the input and V in tilde of S is the output. Now let us go to output impedance. We have Z out of S, and the input is, what is the input and what is the output?
I naught is the input, V naught is the output.
Okay. Also there is a minus sign.
Yes, minus is there.
So if I naught is the input, we'll have minus into V naught. So I'll use a different color so you can remember. Now output impedance is done. Now let us go to audio susceptibility. So what is the input and what is the output?
Vn is the input, V naught is the output.
Vn is the input and Vn is the output. Okay. And the final one, control to output transfer. Output is, what is the output here?
V naught.
V naught. So, like for every perturbation in something, it is contributing to V naught of S in some way. Say if there is perturbation in I naught of S, then V naught of S has something. Similarly, V in of S, there is something in V naught of S. D perturb of S, and it is also contributing to V naught of S. So by superposition, I can get V naught perturbation of S condition 1 is equal to Z out into I naught perturb of S, and V naught of S at condition 2 is equal to GVG of S into V in of S, and V naught of S at condition 3 equal to GVD of S into D perturb of S. Agree?
Yes.
So now if I want to write the final expression, I can write the final expression like V naught of S is equal to GVG of S into V in perturb of S plus GVD of S into V perturb of S minus, because there is minus sign, so it is very critical. Maybe I'll use a different color for minus so that you'll remember. Minus Z output of S into V perturb of S. Also, I know that what is V in perturb of S? If we write in terms of another transfer function.
Sir, can you repeat the question?
Uh, I want to also write V in perturb of S into another transfer function because I have only three transfer function. One transfer function is missing, and V in perturbation of S is dependent on the other transfer function which is missing. So which is the transfer function and how can I write V in perturb of S?
I in tilde into Zn.
Zn, yes. So this is I in tilde into Zn. So we have V in perturb of S is nothing but Z in of S into I in tilde of S. So we got the overall expression. So we have three terms. This is the first term, this is the second term, this is the third term. Now we need to write everything in terms of a block diagram. So let us copy paste this and go to the next page. So this is the final expression that we have obtained. Now we are going to draw a block diagram. So let us start with the let me draw the blocks. So okay, so let me start with I in tilde of S. So what will go in this block? Inside this block,
Zn.
Zn of s. And what will be the output?
Vn.
V
V
tilde of
tilde
s.
of s. And then what will go in this block?
GVG
GVG.
of s.
GVG of s. Very good. And say here I start with D tilde of s. What will go here?
GVD of
GVDS.
GVD of s. And then what else is left? Z naught of s. So this is a Z naught of Z out of s. What is the input?
I0 tilde.
I out. I
Yes.
not.
So I write I naught tilde of s. So this is so now tell me the signs, which is plus, which is minus.
Z out is minus. Everything else is plus.
Yes, this is minus, these are plus, and output is V naught tilde plus. So this is the overall block diagram. I think time is less than a minute. If this meeting ends, kindly join back, then we'll proceed with the final topic of today. So this is the overall block diagram in terms of the transfer functions. So in the future or in the upcoming weeks, if this meeting ends, kindly join back. We'll add controller block as well. So in the upcoming weeks, we'll add controller block, and then that will become small signal closed loop block diagram. So that we'll study in the upcoming weeks. So that is called overall small signal closed loop block diagram. So the controller block has not yet come. So if it comes, where will it fit and how it will look? That will be in the upcoming week. So like this week, we are slowly building our knowledge and adding to our existing knowledge, so that whatever is coming, we are adding, and then in the upcoming weeks, we'll design the controller, and then we'll see how the controller block will fit in this, and where will it fit, and how will our overall small signal closed loop block diagram will look like. So we'll be using this in the future, and in addition, we'll add the additional blocks and see how things are getting changed. So is this clear until this point?
Yes, sir. For open loop boost converter, this expression will stay the same, right?
Yes, the block diagram will remain the same, only the inside expressions will change. So this is generic.
Okay, fine.
So Z in of S, GVD of S, GVG of S, Z out of S are different for different converters, but the overall block diagram remains same. Okay. So if you have any further queries, you can ask, else we'll go to the final topic of today's. Any doubts?
No, sir.
No doubts? Okay. So now we have till now we have only discussed regarding normal converter under no modulation as specific. But now what we are going to do is we are going to discuss about a control to output transfer function under current mode control. Say buck converter is operating with current mode control, then how things are getting changed, how the control to output transfer function will change. So now the control to output transfer function in this case may not be exactly same as what we have discussed previously. It will slightly change, and how it will change, and what are its effects, and how to get that expression. That's what we are going to discuss now. But before that, you know current mode control, right? Say peak current mode control. Maybe I should mention peak current mode control. Okay. So if we start with the diagram, we'll have current like this. And this is my I reference. And sir has considered named this as IC. And say this is IL. So we'll consider two assumptions as specified in all the modeling. Sometimes we consider some assumption, and we have to understand when we are making some assumption that will also put a limitation on that. What limitation and how it will impact, that sir will be discussing in the upcoming weeks. So basically, it will put limitation in the in terms of bandwidth that we can achieve because the model is not valid. So that we are going to discuss. So in this case, what are the assumptions? So the first assumption is we'll consider IL of t to be equal to IC of t. So we'll ignore the ripple. So ignore the ripple. So if we ignore the ripple, then what happens? IL of t in the average sense will become IC, right? And second case, the slope perturbations slope, because slope is dependent on V in and V out. So the slope perturbations are negligible. So these are the two assumptions with which we are going to start, and then we are also going to derive the expression. Any doubts till this point?
Sir, how is the IL average becoming IC?
I see, because say if the ripple is not there, it is constant. So then the peak current is like this, and then ripple is ignored, right? So ripple is negligible. So you can say that the inductor current is also closely matching with this, right? So both becomes equal because the ripple is very, very small.
Okay, fine. Understood.
And also because we don't want the slope to be changed much. So slope perturbations are also considered to be negligible. So there is no change in the slope as such. So these are the assumptions with which we are going to start our modeling, and then we'll proceed. And
Slope perturbation means M1, M2, it is
yes,
remaining
yes,
unchanged,
yes,
right?
yes, yes.
Okay.
M1 and M2 are remain unchanged. So first we are going to deal with an ideal buck converter, and then we are going to deal with the practical buck converter. So for this, we need to start from the dynamics of inductor as well as capacitor. So what I'm going to do is I'm going to take from my previous notes some expressions. So these are the expressions, right? So inductor dynamics. So these are the inductor dynamics, right? So I'm going to take the expression which is LDI by dt is d into V in minus V0. I'll ignore this expression. So I can write, or let me do one thing. Let me draw the buck converter diagram. Synchronous buck. Ideal. This is Q, this is Q bar, this is V, this is L, this is C, this is R, this is plus minus V naught. So we are going to start with inductor dynamics. So we know that LDI by dt, LDI by dt is nothing but Q into V or D into V if we take average, D into V minus V0, and there are no parasitic. And then if you perturb it and then consider only AC perturbation because we are talking about AC circuit, then we'll get something like this. L into DIL tilde by dt is equal to, we'll get D into V in perturb minus D perturb into V in, plus, and then the DC term we are ignored, D capital D into capital V. Also, small perturbation, D perturb into V in perturb is also assumed to be 0. So we got minus V naught perturb. So again, you can also say the perturbation is very small. The perturbations are very small. Clear? How we got the inductor dynamics?
Yes, sir.
Now we'll do the capacitor dynamics. So I can say this is my equation 1. Now let us do that. So capacitor dynamics is C dVc by dt is equal to IL minus I0. So now if we simplify the same, we'll get C into dVc tilde by dt is equal to IL tilde minus I0 is V naught tilde by R. And this is my equation 2. Clear?
Yes.
Okay. And then because of the current mode control, we know that IL tilde is basically becoming IC tilde. And this is our equation 3. Because we are considering IL average is becoming IC. So basically IL and IC are same. So from this we will get any perturbation in IL should also reflect in IC because both are assumed to be same. So we will get IL tilde is nothing but IC tilde because we have assumed both to be same according to our assumption. So from this we got 3 expressions. So one is this, and another is this. Any doubts until this point?
No, sir.
Okay. So now what we are going to do is, in the same way how we have drawn the equivalent circuit diagram, we can also draw. But before that, I want to highlight one thing. Here the control to output transfer function is from the current reference. So here the control is the current reference because it is current mode control. So the control to output transfer function, control to output transfer function is current, right? So this current is the control input and output is V naught. So here our GVC of S is defined as V naught tilde of S by I naught tilde of S. So I need to find that expression where I will have only V naught of S as well as I naught of S. In the case of buck converter, you can directly get from here because IL is IC and GVC is nothing but V naught, right? So There is no
Sir, is it IC or I not in the denominator?
this one IC. IL is IC. IC is the current
Okay, in
reference. This current reference.
the next page, GVC.
Oh, sorry. Yeah, you are right. Okay, thanks for correcting. This is IC. So IC of S. So in the case of buck converter, what happens is you will get an equation where you have an equation in terms of IL as well as V naught. So this equation is redundant. Only using these two equations, I can get an expression which says, or let me copy this. So from these two equations, I can get a single equation that says C into dV naught tilde by dt is equal to IC tilde minus V naught tilde by R. So in the case of buck converter, things will become simpler because I directly have an equation which is dependent on this V naught and IC, and it is obtained from equation 2 and 3, and equation 1 will become redundant. But in the case of buck converter, other converters like boost or buck boost, what you basically have to do is substitute d tilde from equation 1 to equation 2. So in the boost converter, what happens is here you will get one d-part-up dependent expression or term. So you need to know what is d-part-up, right? So that d-part-up will come from here, and you need to substitute that d-part-up in this expression in order to eliminate that. But in the case of buck converter, what happens is you don't have that expression. So d-part-up expression is not coming over here. So because of this, the equation 1 is not needed in order to get the control to output transfer function in the case of buck converter. Whereas for boost as well as buck boost, you need to substitute d part from equation 1 in equation 2 in order to get an expression which consists of I naught as well as IC. So is that clear? Why here things are simpler? Whereas in the case of boost converter, you need to do some more calculations.
Yes, clear, sir.
Okay. So now I can consider this expression, and I can draw the circuit something like this. So you have a capacitor, you have a resistor, and you have a current source. So this is capacitor, this is resistance, plus minus V naught tilde, and this is IC tilde. So in another way, or in a simpler way, what I can tell is we are assuming that IL is equal to IC tilde. So basically IL is a constant current source because IC is constant. So what I can do is in the very first figure that we have obtained, I am replacing the current, I am replacing the inductor by a constant current source. So this will become constant current source IC tilde, and then this remains same. And I don't have I naught tilde as of now. So basically inductor is replaced by a constant current source. So if this is a constant current source and we have an impedance over here, then V naught tilde is what? This impedance into the constant current, right? So which is also what we are getting here. So constant current source, the inductor is replaced by constant current source. And here you have the output capacitance as well as resistance and V naught tilde. So now V naught tilde by IC tilde, which is my GVC of S, is nothing but this impedance, right? Which is 1 by SC parallel R. Clear, or is it a little bit confusing? Is this clear, or is it a little bit confusing? Then I
Sir,
can
a bit
explain.
confused, sir. Can you just explain once more,
Okay,
please?
okay. So maybe I'll just start from the very beginning, and then I'll explain. If you have further queries, then you can ask. So here we are considering a buck converter operating under current mode control. with a constant reference. So it is basically in a inner closed loop because the inside loop is closed. So IC is constant. So I can say that this is inner closed loop. Because current mode control has two loops. One is the output voltage loop and the inner current loop. And the inner current loop is closed. So we have a fixed reference IC of T. And then we are perturbing the IC of T. And then seeing how V naught of T is varying. So that's what we are doing. So that is the control to output transfer function here. The input control input is the current reference and the output is V naught perturbation. So that is the overall objective in this question. V naught perturbation of S by IC perturbation of S because it is current mode control. So for this, or in order to get this, we have started with few assumptions. One is we have ignored the inductor current and in an average sense, it will become same as the IC of T. So basically, inductor doesn't have ripple and it has a constant current. So inductor is acting like a constant current source, and we can also get the IL perturb as IC perturb because of this assumption. And we also have as a assumed that the perturbation in the slope is negligible, and also all the perturbations are very small, so that product of two perturbations can be ignored. So we have started with the ideal converter because the first is ideal buck converter, and then we got the inductor dynamics. We have perturbed, ignored the DC terms because we are only worried about the AC terms. So we have removed the DC terms. Also, the product of two perturbed terms is also assumed to be zero because of the third assumption. We got one expression here. Capacitor dynamics, we got another expression here. These two are what we have discussed in the previous week, but again, we have written. And because of this current mode control, the inner closed loop current mode control, we have assumed inductor current is ripple free and equal to the reference. So IL perturb is IC perturb. So we got three equations, and the objective is to get V naught perturb of S by IC perturb of S. So you need to have an equation which consists of only V naught perturb of S and IC perturb of S, no D perturb. So you have to eliminate D perturb. So in the case of other converters, you will have D perturb in two equations, this equation as well as this equation. So you need to obtain D perturb from one expression and substitute it in the other expression. But in the case of buck converter, there is no D perturb in this expression. So this equation is not needed in order to get GVC transfer function. So we will be needing only 2 and 3. Whereas in the case of boost converter, how sir has solved in his lectures, sir gets D perturb expression from equation 1 and substitute it in equation 2. So he will eliminate D perturb in the equation 2 and he will get a single equation which consists of V naught and IC perturb. Whereas in the case of buck converter, things are simpler. So that's why we need only 2 and 3. Equation 1 is not needed because equation 2 doesn't have D perturb related term. Now using these two equations, we got this expression. So now if we write this expression in terms of a circuit, like how we have done in the circuit averaging, we have a capacitor, we have an output, and then we have a constant current source. So this is the overall circuit that we got for a buck converter, ideal buck converter, operating under constant reference, fixed reference. So basically, we have considered that inductor is ripple free and inductor is equal to constant current source, right? That is the assumption. So what has happened in our original circuit, whatever we have, the inductor we have replaced by a constant current source. So that's what we have obtained. So you can either assume that the inductor is a constant current source and then redraw the circuit, or you can also get these equations individually. And from that equation, this is the circuit that we have obtained. So if you still have confusion, please ask, don't hesitate. This might be a little tricky to understand. So if you have any further confusion or queries, you can ask.
So just one basic thing.
Yes.
In the previous thing, we have considered control to output as V naught perturb by D perturb.
perturb,
But here we
yes.
are considering it V naught by like IC. Why is that, sir?
Yes, okay. So in the previous case, when there is no control, okay, or maybe I should explain in two things. So there are two control methods that we have learned. The case of current voltage mode control and then current mode control. So in the case of voltage mode control, what happens is we are comparing the VRAM with V control voltage to get the duty ratio. Whereas in the case of current mode control, we are comparing the inductor current with the current reference IC and inductor current IL. So here the control input is duty ratio D, which is nothing but V con by Vm, assuming the maximum voltage of the ramp is Vm. Okay, say Vm is 1, sometimes Vm is 1. So it is V con. Now here GVD is nothing but V0 perturbation by V con perturbation or V0 perturbation by D perturbation. However, in this current mode control, the control input is here, the duty ratio is generated from the Vcon. So V0 by Vcon is our control to output transfer function. Now we are in the closed loop. Till now we have discussed open loop. So in the above four transfer functions where we have discussed, that is open loop. So duty ratio is the input. There is no controller. Here the controller is giving us Vcon. So my control input will become Vcon. So now the control to output transfer function is V0 by Vcon perturb. But in a case when Vm is equal to 1, Vcon is becoming D perturb. So in that case, my control to output transfer function is V0 by D perturb. So usually we denote control to output transfer function as GVC. But in the case of voltage mode control, Vcon will become D when Vm is 1, when the ramp is having a voltage of 1. So V0 by D perturb is nothing but our control to output transfer function. Whereas in the case of current mode control, our control input is reference, because here we are comparing the inductor current with IC. So here our IC is the control input. Because my duty ratio, the duty ratio is varied depending upon my IC. So the duty ratio is coming from IC and I am not directly generating the duty ratio. My controller output is IC and that is passed through modulator to generate the duty ratio. Here also my control output is Vcon. So whenever we say control to output transfer function, which is GVC, here it is V0 tilde by Vcon tilde, and here it is GVC equal to V0 tilde by IC tilde. But in the case of voltage mode control, there is a dependency, direct dependency. If this becomes 1, my V0 tilde by Vcon tilde will become V0 tilde by D tilde. Whereas in the case of current mode control, it is not directly related, but it is kind of related. So what I can do is say this is my IL1, then my D perturb is nothing but IC perturb minus IL1 perturb by slope M1 into M1, right? M1 T. So my D perturb is not equal to IC perturb. So my GVC is not equal to GVD. Only in the case of voltage mode control, my GVC will become GVD if Vm equal to 1. However, the control input is Vcon. So the control to output transfer function is V0 by Vcon perturb. In the current mode control, the control to output transfer function is V0 by IC perturb. So we have to always check what is our control input. Here the control input is Vcon. Here the control input is IC. So my control to output transfer function is V0 tilde by IC tilde. So that's why we are not considering D tilde. Instead, we are considering IC tilde because it is peak current mode control as specified in the question.
Got it, sir. Thank you.
So now if we push this down. So this is my overall circuit diagram that I have obtained. So now if I have to calculate V0 tilde by IC tilde, I can directly write it as R parallel 1 by SC, which is R by 1 plus SRC. So I can write my GVC transfer function is nothing but R by 1 plus SRC. So this is for ideal case. Okay, so this is for ideal case. Let me make some space here. Okay, so this is for ideal case. So in the case of non-ideal case, what I can do is IC tilde RC 1 by SC R plus minus V naught tilde. So now here we'll have GVC of S is equal to RC plus 1 by SC parallel R. So this is for non-ideal.
Sir,
Non-ideal
REQ will not
practical.
come into this picture.
No. So even if say there is REQ, good question. Say let us assume there is REQ. So you know that it will come in series with the inductor. So I can write it something like this. So this is my IC tilde and say this is RE. So now this is my IC tilde. And now if I am considering this entire thing as my impedance, so RE is not coming into the expression because my if I come like consider this as a single impedance, which is RC plus 1 by SC parallel R, IC is flowing through that. So my V naught tilde is this impedance into IC. So V naught tilde by IC tilde is this impedance, and RE is in series with the current source, so that will not affect V naught tilde, and that's why REX effect is not coming over here.
Okay.
Is that clear?
Yes, sir. Clear.
Okay. So yeah, so this sums up what week 6 is about. So the like towards then maybe it is a little bit tricky because suddenly we move to the closed loop current mode control. So there is a jump from there. So I understand that, but because sir has covered, I have discussed it. But with time, with the upcoming weeks, it will become more clear when we also learn about the controller and the closed loop. We'll see how voltage mode control, small signal, this block diagram will differ from the current mode control. So there is significant difference between voltage mode control as well as current mode control when it comes to the block diagram because both have different dynamics. In the buck converter, this will be second order, this will be first order. That we'll discuss in the upcoming weeks. But this week is all about bridging, bridging that gap between previous week and the next week, which is about getting the transfer functions and understanding them and how we can derive them using the small signal model and how we'll use them to design the controller in the upcoming weeks. So we have discussed about the AC equivalent model to start with, and we have also discussed how DC equivalent model and AC equivalent model have their applications and how they are different and how they'll help us to analyze different aspects like operating point efficiency, losses, transfer function, controller design, and transient performance. Once we got the AC equivalent model, we have understood what are the significance of these different transfer functions and how they are defined and how to get those transfer functions. So first we have to the steps are first we have to identify which transfer function we are being asked, and then we have to define, we have to write the definition of that, and then we have to remove the other terms perturbation from the circuit and redraw the circuit and then get the expression. So the same thing, same step by step guidelines we have followed for all the transfer functions and we got the expressions. If there is practical buck converter, then there will be parasitic. but the entire process remains same. Only thing is the expression will be a little bit complicated because of the additional parasitic, which I have not derived, because you can derive, it's just mathematical calculation. So I have given the expression though, so you can simplify later and cross check with the expression that sir has obtained. And then we have also discussed about the small signal block diagram. So we have drawn the individual block diagram and then the expression, and then we have combined all the block diagram to get the overall small signal block diagram. In the upcoming weeks, we'll also add the controller block and see how this block diagram will vary for voltage mode control as well as current mode control. However, in this week, current mode control is also covered with inner closed loop, which means constant I reference. And then we have seen how to get the control to output transfer function, because here the control input is I reference. So the basic difference between voltage mode and current mode control is, in voltage mode control, the control input is Vcon. So the control to output transfer function is V naught tilde by Vcon tilde. However, Vcon tilde will become D tilde if my Vm is 1. Say if my Vm is not 1, then they will not be equal, but there will be a scaling factor. In the case of current mode control, the control input is IC tilde. So my control to output transfer function is V naught tilde by IC tilde. And that we have calculated for both ideal as well as non-ideal buck cases. Similarly, for boost converter, there will be one RHP0, but I think that Kelvin has covered, so I'm limiting to buck converter. So this is all about week 6. If you have any further queries, you can ask.
Sir, there are some concepts related to Q, ZC, alpha, and all those things, time domain things. Was that covered in the other lectures, or like that we covered later?
Okay,
or something?
Q, ZC, and alpha. So they are the terms that sir has used. So I think alpha is R plus RC by, you have to check, alpha is R plus RE or RC by RE or RC, that you have to check. And Q is defined as quality factor. So whenever there is a Bode plot, like you get this peaking, right? Either like this or like this or like this. So it decides whether it is underdamped, overdamped, critically damped. So Q is used, either Q. Sometimes they also use zeta. So Q and zeta are related. And ZC is the square root of L by C. So these are the terms that are used to write these expressions, these complicated expressions. So sir has simplified those expressions. So here you will get a complicated expression. So sir has used this terminology and written in this terminology. So in the slide sir has covered, because I have not written the final expression, I have not written this. So this is called critical impedance, which is square root of L by C.
Okay, fine, sir. Thank you.
So if others have queries, they can ask, else we can wind this session here.
Sorry, one more thing. That
Yes, yes.
omega RHP for different converters, that
Yes.
also like not derived here. Like I'll
No,
just
no,
check
no.
maybe the lectures.
Yes, I have not derived, because in buck converter there is no RHP0, but Kelvin has discussed boost converter where you will get RHP0. Similarly for buck boost converter. So in Kelvin's lecture or Sir's lecture you can go through. With boost converter as well as buck boost converter, there will be RHP0. So I think that he will have covered, because in buck converter there is no RHP0. I have not discussed that all.
Okay, I'll go through that. Thank you.
Yeah. Okay, then with this, I'll end this session here. I wish you all the best. And in the next week, me and Kelvin are interchanging the classes, because he's busy on Tuesday. So he'll take the class on Monday. I'll take the class on Tuesday. So links are same. My link you can use to join on my session. His link you can join to join his session. And we'll be discussing buck as well as boost, so that you can we can have detailed discussion in buck as well as boost. So with this, I'll end this session over here, and I wish you all the best. See you on next Monday. And good night, everyone. This is a very nice session, and thanks for joining and making it very interactive.
Thank you, sir.
Thank you.
Thank you, sir.
Thank
Good
you.
night.